Okay, now for the big daddy. This is the spectral theorem, which is the single most important theorem in Eigenland. And it basically tells us how we can take any square matrix that's not weird and decompose it into its eigendecomposition, which is essentially its eigenvectors and its eigenvalues working together. And this allows us to see all the way deeply into the matrix as to what it's ultimately composed of. Okay? So here's the spectral theorem. And I'm telling you what, this thing has E equals mc squared level significance. Here's what it says. Any, I lied, almost any, meaning not the weird ones we talked about before, but putting that out to the side for a moment, any square matrix M, we'll call it, can be expressed as the product of three other matri, or matrices. And they are traditionally called V. Lambda, that is a capital Greek lambda. Okay, so I know it looks like an upside down V. Maybe that'll help you remember it. But that is the capital letter lambda. We'll see why in a minute. Times, also V, inverse. Okay? Now, what are V and what is lambda? Here's what they are. Let's say we're dealing with a 4x4. I'll make this concrete. So let's say M is a 4x4. It's got 16 entries here, right? And we know that since this is not a weird one, it has 4 distinct eigenvectors, each with its own eigenvalue. So I'll just call them x1 through 4, and each one has its corresponding eigenvalue, lambda 1 through 4. 1, 2, 3, 4. I can count. Okay? Here's what V is. V is a 4x4 matrix that has all of the eigenvectors in it as columns. Okay? So take all of the eigenvectors, each of which is a 4x1 vector, and arrange them as columns on this thing, and you have V. Now, what is capital lambda? The reason we use the letter lambda for this is because this is a diagonal matrix which has the eigenvalues. So all these are zeros up here, all these are zeros down here. And then this, of course, is just the inverse of V, right? We use the same letter V, V, and that's because these are the same matrix. So basically we just take all the eigenvectors and we find the inverse of it. How? Ask Python. How do we know what the eigenvectors are? Ask Python. How do we know what the eigenvalues are? Ask Python, or R, or your favorite programming language. Okay? But this here equals M. Now we're going to play around with this equals when we talk about video compression, because by restricting the number of eigenvectors we use, we're going to be able to make this an approximately equal that's going to turn out to save us a ton of bandwidth on the internet as we play our video from Netflix or whatever, okay? But right now it's an exact equals thing. And essentially what this is doing is it's saying if you have M, which looks like a mess of numbers, essentially if you figure out what the eigenvectors are, then this is essentially the operation of it. So what it's saying is that we want lambda 1 of the first eigenvector, lambda 2 of the second one, lambda 3 of the third one, lambda 4 of the fourth one. And if you look at the eigenvalues and how they are expressed in terms of how their magnitude is with each other, you see how important each eigenvector is. So for instance, let's say that lambda 1 turned out to be 15. And let's say lambda 2 turned out to be 3. And let's say lambda 3 turned out to be 1. And let's say lambda 4 turned out to be 1/5 or something like that. Okay? What this tells you, and we'll see this when we look at the eigen applications, is that almost all of the matrix is concerned with the direction of its first eigenvector. All this stuff down here has diminishing returns on the value that the matrix is going to map a vector to. It is extremely strong in its dominant dominant eigenvector direction. On the other hand, if we said, well, this was 5, and this was 4, and this was 2, and this was 1, now they're all contributing more equally to the operation of the matrix. Unlike over here, where basically the dominant eigenvector was the only thing that mattered, here all the eigenvectors kind of matter. If we take the top two, we've got most of it. If we get these bottom two, we're sort of getting a little bit more detail here. Now, I know it's hard to visualize because you're like, what does it mean to only take a couple of eigenvectors or whatever, right? So we're going to see that when we look at the eigen applications in the next episode. But the spectral theorem basically tells us that any matrix we can decompose, again, it's called its eigendecomposition. We have diagonalized the matrix by doing so. We call it diagonalizing because we've sort of turned it into a diagonal matrix. We've taken it and said, as long as you're using the eigenvector basis, as we'll talk about in a minute, as long as you use the eigenvectors to describe the directions that are important to this matrix, then the actual oomph that the matrix has in each of those directions is expressed by a simple diagonal matrix. All zeros, except on the diagonal what the different eigenvalues are. Okay? And that is going to allow us to do a lot of amazing things. So, see you next segment.